So now that we're familiar with permutations from the point of view of group theory, in this video, we're going to look at ways of representing permutations and sort of ways of finding them in mathematical nature, kind of cooking them up. And as you can see here, we've already got our notes spelled out in some degree of detail. And so we're going to just kind of talk through this. So to get started, let's say we have a simple set here, right? 4 elements in set A. And we have 2 permutations. We have this permutation F, which eats 1, 2, 3, and 4, and gives us these outputs, 2, 4, 1, and 3. And another permutation G, 1, 2, 3, 4, with these outputs, 1, 3, 4, and 2. The first thing that I think when I see this is, man, it's a bit of a nuisance to write down the inputs and outputs so explicitly. It's kind of a lot of information to take in. And so towards streamlining it, the very first thing that we could do is organize this into a nice 2-column chart here. We got they're not 2 columns, 2 rows, where we have inputs on the top, outputs on the bottom. And this is, well, it's a little bit more compact than this previous representation. And it allows us to compose permutations in a relatively straightforward way. It's basically just looking the information up. But since I've represented it nice and compactly, what I can do is just fish up the inputs and outputs from the individual pieces and plug one into the other. So what I mean by that is, for this first guy here, we have 1, 2, 3, 4, a set of inputs. And then if I do F first, 2, 4, 1, 3, you see I've got these written here. Then in order to calculate F following G, I went and I took G, and then for each output, I grabbed the corresponding input and wrote it underneath. So 1 goes to 2 by F, and then 2 goes to 3 by G. So 3 goes down here. 2 goes to 4 under F, and 4 goes to 2 under G. So you see I did that for each possible thing, and then I just scratched out the line in the middle because I'm not interested in that anymore. And now I have this input, 1, 2, 3, 4, and these outputs, 3, 2, 1, 4, representing the entire combination of G following F. This notation is pretty helpful when you're dealing with a relatively small number of elements and you just need to see where something goes pretty quickly. Especially true if there isn't like some other kind of context that might give you a different way of thinking. And I'm going to show you one such example below. Namely, permutations that come from geometry. And so if you're dealing with algebra in a geometrical setting, or you've been inspired by geometry to do algebra, I guess you'll see what I mean by that in a moment, then oftentimes it is more helpful to think with our visual brain whenever we can. And here we're going to start doing that. So what you see is if I have a square here with vertices A, B, C, and D, I can think about rotations on this square, which are permutations of the 4 vertices A, B, C, and D. If I rotate everything 90 degrees clockwise, each vertex is shuffled along 1 step. And so we can think of this as a permutation, but also as a rigid motion of geometry. So we see where A goes, D landed there. Where B was, A landed there, and so on. So we have the input vertices and the corresponding output vertices, which are the vertices that land in the position that vertex came from. Now, to be clear, you don't really have to write them this way. We could just as well have said A goes to here, and that's where B used to be. So we could make the opposite collection of associations if we wanted to. It doesn't really matter which one we do for the purposes of this discussion, but when you're, doing geometry and doing algebra, you want to know which way you did it. And so I call your attention to this. Now, the nice thing about thinking with our geometry brain is that we're very familiar with shapes, right? The symmetries of shapes. We know that squares have basically 2 types of symmetries. They have the rotations we just talked about, and they also have reflection symmetries, one of which I have depicted here for you, where we can switch, A and B and C and D in pairs. And with this in mind, we can think about compositions of symmetries in the same way as before, but now we can draw a nice little picture of it. So if I do a reflection, that's encoded by this, right? A and B switch places, these 2 switch places, D and C switch places. And then up above, we saw what the rules for the rotation were. The rule was every letter goes to the previous letter. So B goes to A goes to D goes to C, and C goes to B. And so this gets me a permutation whose vertices running counterclockwise are labeled around the box with A, D, C, and B, like so. And so we could ask ourselves, what kind of symmetry is this? Is this something that we already know about? Is this a group? And the answer is yes, that the symmetries of a square do form a group. They are a subgroup of the permutations with any four symbols. And the reason it has to be a subgroup is because, well, some permutations are not possible. So, for example, let's look at this one because this is here the letters are in order, easiest to see. A always has B and D as neighbors. No matter what I do to it, when I do a reflection, I do rotation, I do these diagonal reflections, the neighbors of A are always D and B. You can never make C a neighbor of A. And so it is not the case that the symmetries of the square are equal to the permutations of four vertices, but rather just a subgroup. So we denote this by writing that the symmetries of the square, which we're going to call D4, are a subgroup. We use this triangular lesser equal kind of sign for S4. And this is the group theory version of being a subgroup. We want to distinguish it from the usual subset notation so that we remember we're talking about groups. Now, one possible question is why D4? If we go back to our symmetries, I mean, I'm claiming here that there are 8 such symmetries. That's what the absolute value bars mean. It means that the total size of D4 is 8. We can convince ourselves that that's true. Maybe one way to see this, what's the easiest way to see it? Looking here, we can see that there are 4 possible rotations because you can rotate 90 degrees at a time. And after you go 360 degrees around, you're back to where you started. But we can include that because that's the neutral element, right? When you do a full 360 degree turn, you've changed nothing. And every group has a neutral element. So that's 4 elements. We can also see that there are 4 possible reflections, right? You see one of them here, which exchanges A and B and C and D. We can do the same thing horizontally and exchange them, the other 2 pairs, A and D and B and C. That's 2 reflections that do not pass through any vertices, but there are also 2 more reflections that pass through the diagonals, right? The ones that just swap B and D or that just swap A and C. And I'd let you guys take a moment and work through the group table. You could maybe pause the video here and you could write down, given those 8 elements so far, you could try composing them and you could look and see if there are any other possibilities. And what you're going to see is that the answer is basically no, because of this business of counting where the neighbors go. And I'll talk about that more in just a second. So towards this, we have this question, which is why D4 as the symbol and not D8 when you have 8 things? The reason is, actually, as I'm seeing, I notated this already. There are 8 possible symmetries. I've listed them out here again, 4 rotations and 4 reflections. But we're going to call this D4 just because, well, it seems easier to remember that there are 4 vertices and there are 4 symbols. So D4 is a subgroup of S4. And just then in general, we can use that notation for all polygons. So if you want to talk about like a pentagon or like a decagon, then we can say, D5 for the symmetries of a pentagon and not be confused about whether or not we're talking about the shape or the size of the group. So in order to convince ourselves another way that there are actually 8 symmetries in this group, let's finish the logic from before. So here I have a box with unlabeled vertices. Where can I place A if I'm using rigid motions? What choices do I have? Well, the answer is A can go anywhere. I can place A into any of these 4 guys by doing some kind of rotation. After I've placed that A, how can I place the neighbors? Well, the neighbors have 2 choices. I can place B and D in their so-called orientation preserving orientation. I know it's a little bit of a mouthful, but I can place B to the right of A, clockwise from A, or I can do a reflection. And if I do the reflection, then B and D switch places, and that's orientation. We would call that reversing. And so, therefore, there will be 4 ways to place a vertex, 2 ways to place the neighbors, And you can see that that's everything, because once I've placed A and its neighbors, C only has one choice for where to go after that. Moreover, if I was doing this with a bigger shape, like say a hexagon, the same logic would still be true. After I place my vertex A, I would have 6 choices for where that goes, and then I have to decide what to do with the neighbors. If I decide that B should go to the right of A, then the same logic applies to C, right? Because B has neighbors A and also C. And so if B is to the right of A is to the left of B. If A is to the left of B, C is not to the left of B, C is to the right of B. And so that tells me where C goes. And then C tells me where D goes, and so on. So the only choices are, where do you put a vertex of your choice? And do you do an orientation flip, or do you keep the orientation the same? In other words, is it a rotation or some kind of reflection? And since that's the only choice, you can just multiply these together. And you can see that the number of ways for a hexagon then is 6 times 2, or 12. So all in all, what we're getting out of this is we're seeing that we now have a couple of different ways of thinking about permutations in group theory. We have the input-output notation, which is very helpful when you don't have a mental picture. But when you do have a mental picture coming from geometry, you have all of this extra stuff that comes up because we know something about how geometry goes. And so going forward, we're going to be leveraging our geometrical intuition whenever possible to get a good grip on how groups work.